Today, we're introducing two speakers today, and we're going to hear about supernova, correlated supernova, why they explode, and how can machine learning help us find out the answer, and a little bit about why neural networks are so bad at finding geometrical relations. So we have some more people coming in. Come on in, sit down, we're starting. The first speaker is David Vartanyan. He's a Hubble Fellow at the Carnegie Observatory. And he's having a flash visit today. So if you do want to catch him today, maybe use time after this talk. I have a spot to talk to him, but I have to give others the opportunity because he's leaving today.
Yeah, me too.
And he is going to tell us about supernovas and core collapse explosions and how machine learning and high performance computing can help in figuring these objects out. David, the floor is yours.
Thank you. Thank you, Rafael. Thank you to the organizers for inviting me. And thank you everyone collectively and individually for the courtesy of your attention. It's a pleasure to see familiar faces and new faces too. I'm David Vartanyan, and today I will be serenading you about recent developments in the explosive deaths of massive stars, colloquially known as core collapse supernovae, as they lie at the intersection of machine learning and high-performance computing. Supernovae are important to understand for many reasons. On cosmic scales to microcosmic scales, they shape galactic feedback, and they source the carbon atoms in the sandwiches you're enjoying right now. But for the better part of half a century, supernova theory has failed to explain how these stars, which we very much observe for better or for worse, exploded. In the last decade, this paradigm has been transformed from a schema where stars would collectively fail to explode along global collaborations to now, where we have not only the first exploding stars with different groups, different codes, different methodologies around the world that produce not just explosions, but robust explosions whose early diagnostics are consistent with general observations, including energies, nucleus-sized yields, remnant masses. And so the field is ripe right now to push the envelope a bit further. And in my talk today, I will be doing this in twofold. First, we're now afforded the luxury of asking why these stars, as they explode, why do they explode? Which models do and which models don't? In the last few minutes, I'll also give a higher level overview of prospects for intertwining core collapse supernovae theory with the future of observations. I want to just cater to you one of many movies you may have seen. Adam Burrows visited last week, and he gave you an appreciation of the details of the supernova problem and a whole buffet, a litany of results. This is the explosion, a radiation hydrodynamic explosion of a 25 solar mass per gender, first in the inner 100 kilometers, and it zooms out at the end thousands of kilometers. The important things to note here are the explosion is very robust and very asymmetric. The particles you see falling in are just tracers we follow that can then determine the electron fraction evolution, the elements you produce. But on timescales of, this is where we are right now, timescales of half a second to timescales of around 5 seconds. The supernovae we observe are timescales of days to months to years to centuries. How can we bridge this gap? First, I want to give you a quick overview of the results that we've arrived to using our code Fornax in the last decade. These are neutrino-driven explosions. I'll talk more about this in a second, but there's no need to invoke rotation or MHD to explode garden variety core collapse supernova. We now have a sample of around 2 dozen, now almost 3 dozen simulations. These are more than all other 3D efforts combined, gone out to the longest times, out to 10 seconds, with explosion energies that range from 1/10 of a beta to several beta. A beta is 10 to the 51 ergs, or an FOE, a FO. For the uninitiated, an erg is the amount of energy it takes an ant to do a push-up. An ant has a mass around a centigram and arms around 0.5 millimeter. We also have early prediction of the remnant masses you form but neutron stars out to black holes populating below around 1.3 solar mass lower mass neutron stars and above 2, 3, and possibly 5 solar mass black holes. And we'll say more about that in the coming months. You form an early spread of kicks and induced spins that can range from tens to thousands of kilometers without any initial rotation. The turbulent accretion you saw in the first movie can coherently convect momentum onto a central object, both linear and angular momentum, and drive high kicks and high spins. We can also see early estimates for nickel yields, shown on the y-axis here against explosion energy, we see strong evidence for these early trends of observables of parameters of these explosions as constrained by the properties of the progenitor. And we can now also see the earliest templates. In work done with Lala Choi, an undergraduate at Princeton, we developed early spectrograms that determine how well can we detect a fortuitous galactic supernova event in gravitational waves. And if it does go off, you can see here in these, the colored noisy lines are estimates from our simulations, and the solid lines, these dashed lines, are the different detection curves for various instruments from LIGO, VESIGO, out to the linear gravitational wave antenna. If a supernova goes off in the Milky Way, we will be able to detect it in almost 5 decades of frequency space, independent regardless of its progenitor mass. Early efforts that looked at the secular components of gravitational waves, which we call the memory, that are sourced by both matter and the neutrino asymmetries, can push this horizon out to tens of kiloparsecs out to a few megaparsecs.
And David, sorry for ignorance. What is the origin?
Yeah.
Origin of gravitational waves in this core collapse supernova?
Yeah,
What's actually happening that produces gravitational?
That's right. I'm glad you asked. There's a whole host of mechanisms that drive asymmetries. You can have rotation, you can have hydrodynamic instabilities. The dominant source in our models for the kilohertz frequencies we see are astroseismic excitation of the PNS by turbulent accretion. The low frequency memory component you see is due to large scale ejecta that evolves on longer timescales, hence the low frequency. And you can also see contributions from neutrinos, which are also on secular timescales. But the dominant kilohertz contribution is from turbulent accretion. Yes. Yeah, so SASI is that standing accretion shock induced instability. I might have forgotten to add a word in there. But SASI has been introduced a bit controversially in history to explain why stars can explode. And essentially, when you have a stalled shock that stalls close enough to the PNS, your proto-neutron core, you can drive advective acoustic oscillations of matter falling in and bouncing off the PNS. And these can contribute to deformations of the shock. However, the contributions to the explosion can be marginal. They may be important for massive stars. The SASI does appear in our models that fail to explode and can have a distinct signature at around 100 to a few hundred hertz that it can hear. Whether it contributes to explosion outcome seems likely not, but it may have an important role for selection models. Another important point is you can actually hear these signatures because they are in the kilohertz bandpass, so they're audible to our human ears. Hopefully this is. All right, if it's too loud, I apologize. If it's too quiet, I also apologize. You'll hear that big. Okay, let's hit too quiet. So you'll hear first a sonified gravitational wave signature from a non-rotating star. Now, the following is for a rotating star. You can hear a chirp in the latter case at very early times. That's due to correlate oblate oscillation of the PNS due to rotation, which contributes to a distinct signature at core bounce, which would be absent without rotation. 3D convective effects can also contribute to this. But these signatures will be detectable by future instruments if you're fortunate enough to have one in the galaxy. And if we have these instruments primed for extragalactic detection of core collapse supernovae, low frequency memory effects can also extend the detection horizon. But I don't want to get too much into the details there. These are just early forays. Gravity waves. We can also see neutrinos from core collapse supernova, and there's a litany of instruments being developed to do just this. On the top, I should mention results from our series of multidimensional simulations. We see early correlations, like we saw for nickel mass and explosion energy, with neutrino properties and core properties of the progenitor. On the top, I plot the neutrino luminosities for a series of models against the time after bounce. And you find that cores that are more compact, that means they have a higher mass over a given central radius in the interior. The density is more centrally confined, have neutrino luminosity plateaus that last longer. So you have this sort of Phillips-like relation for type 2 core collapse supernovae neutrino luminosities. Again, that here illustrates early correlations. We also see correlations between the neutrino signatures emitted and the core mass and radius. Here, our core mass and radius is a strong correlator predictor of the emergent neutrino luminosities and vice versa. And if we have joint detection of neutrinos and gravitational waves, we will have unprecedented novel constraints on the nuclear equation of state, which is very tenuously understood, and new constraints on the interstellar mass and radius. We can also get constraints on neutrino oscillations and a whole host of physics. But the idea here is just to illustrate an early assembly of correlations that emerge naturally between explosion diagnostics and core properties. No, I want to just, yes.
Which equation of state we use for your simulations? Just for
Yeah, so the equation of state that we use is the SFHO, the standard equation of state, which is, as of now, the surviving EOS that is marginally consistent with all known experiments, both theoretical and laboratory. And I'm happy to just go on a tirade about this because there's a lot of nuance here, but it is the equation of state in nuclear context is very poorly constrained. So in the last 6 years, there's been an influx of early, and in our case, often naive attempts to apply machine learning to the core collapse problem, because we now have enough simulation to have a training set. A lot of this has been focused on accelerating the complex neutrino radiation hydrodynamics, which is the bulk of the simulation time. If you can get factors of 2 to 10 speed up in the simulation, you can get 2 to 10 times more simulations. There have been also early efforts to look at physics-informed predictions from core collapse supernovae, and that's what I want to talk about today. The motivation is simple. Now that we see stars explode, can we know why they explode? I addressed this first in a paper in 2018, where we took a series of 2D simulations done by Fornax, and we then try to predict which models do and don't explode, amongst other things. These are, again, using the SFHO marginally consistent equation of state. We have around a dozen models here, and I show the shock radius on the top left. As the core collapses, it triggers a shock that propagates outward. The shock eventually stalls at a few hundred milliseconds. The addition of neutrino heating can revive a stalled shock into a successful supernova explosion. We see some models explode and some don't. That's a 0th order observation. There is no clear trend between model mass, indicated from 12 to 25 solar masses, and explosion outcome. It's not like collectively low mass stars all explode and high mass ones fail to do so, or vice versa. That's been well understood for some time. And so to resolve why certain stars explode and others don't, we just took a step back and we looked at the initial conditions shown on the bottom right. We show here on a log scale the density against the enclosed mass in the inner core, out to the inner 2.5 solar masses. And I show here in a dotted ellipse, some models have a sharp feature where the density drops by a factor of several, almost immediately in mass. This corresponds to a compositional interface, namely the silicon-oxygen nuclear burning interface. Models that have a prominent interface, and I'll give my conclusion first, all else being equal, being treated with the same equation of state, the same detailed neutrino matter interactions transport. Models with a strong, sharp silicon-oxygen interface, deep within the core, are more likely to explode. The reason for this is straightforward. Imagine you're the stalled shock located around 1.2 solar masses at a chandrasekhar mass. Matter is still flowing in through you. You're stalled. Initially, you see high density matter that powers a high neutrino accretion luminosity behind the stalled shock. And then almost immediately, you encounter this region where the density drops. The ramp pressure drops. And so a combination of a high neutrino luminosity interior for the stalled shock and the region of low ramp pressure exterior for the shock provides a fertile breeding ground for explosion. In fact, we can determine not just which stars exploded red, black, blue, green, the 21, 16, 17, 19, but the timing of explosion. Models that accrete interface earlier explode, and they explode earlier than those that accreted later. Models in the 20 and the 25 solar masses do have a strong interface, but it's just too far out. By the time it accretes, your neutrinos have escaped and you've lost your central engine. And so for these purple and magenta colors, there's a small bump in the shock as it encounters the surface, but it's not enough to drive an explosion.
Is there do you have a cutoff? Like, do you know where exactly the transition happens? How far in? Like,
yeah. So I'll talk about the next slide.
okay,
If it's not adequately addressed, please ask me for more detail. Yes. And so with a postdoc at Berkeley, Benny Deng, we decided to take a early foray at applying machine learning to the core collapse problem. This was a very much hammer meet nail sort of situation. So we took a set of 100 2D axisymmetric simulations, and 2D because it's cheaper than 3D, you can do more models at the later times, and because the key metric we're concerned about here is explosion outcome, which is consistent very, very robustly between 3D and 2D. If it explodes in one simulation dimension, it'll explode in the other as well. And so we have a set of 100 simulations, of which around 70% explode. The ones that don't explode lie within 12 to 15.4 solar masses, which is very much an anti-red supergiant problem. We don't see a red supergiant problem in core collapse server simulations, and I'm happy to talk more about why that is. And so we first applied a simple random forest classifier. This is trained with 5 trees, and each tree had 7 to 10 nodes. And we fed in a series of explosion metrics we'll discuss in a second, based on these 100 simulations we had, and then classified the outcome as either a 1 or a 0 binary. Does it explode or does it not? And we then binned across 5 bins for cross-validation, repeated this for all the metrics. The metrics we can sort of show on the bottom right, and I'll go through them in order. First, we take our density profile that I showed earlier and take a very crude parameterization of it, just the log mean density against the radial coordinate. This is meant to be our null hypothesis. And this, shown in the first column in the table on the bottom left, gives an accuracy in predicting explosion outcome of around 70%. So even this null metric can predict explosion outcome because the density encodes information that will determine whether the star explodes or not. We then take in a series of 2 parameters that have been used historically and often also incorrectly to predict explosion outcome. These are first compactness, and second,
These are the features that you fed to the random forest.
That's right.
And so what is your accuracy for each of these features you're presenting here? Sorry, I missed that.
Yeah, so that's right. So this is the accuracy in predicting explosion outcome. So the true positives versus.
So that's the accuracy that that feature alone has?
That's right. That feature alone has, not in tandem. And these numbers are presented across accuracy, precision, recall, and F1. Yes. And yeah, so first, our null metric gives us around 70% accuracy predicting explosion outcome. Good. We then feed in compactness. Compactness, as I mentioned earlier, is a dimensionless pseudo-potential. It's essentially mass over radius in dimensional quantities that defines how essentially confined your core is. And this surprisingly gives us a reasonable accuracy around 83%. And the reason this is not because compactness is a good metric. It's rather, if you plot here in the top panel, the mass of our models from 9 to around 27 solar masses against compactness, we see that there's no trend between compactness and explosion outcome. It's not like, oh, low compactness models explode and high compactness health would be sort of vice versa. There is no monotonic trend between compactness and outcome. Rather, machine learning is able to find certain clumps in these features that are broadly defined that correlate well with outcome. But again, no monotonic dependence with compactness on explosion. This is simple, but it produces explosion reasonably well. We then apply a second condition called the Earl condition, which may be familiar to some of you. And if not, the Earl condition takes in our definition of the silicon oxygen interface I introduced earlier, and then complicates it with a series of semi-analytical, semi-accurate approximations. And this performs quite a bit worse. It only performs marginally better than our null metric. And the reason for this is that while compactness may oversimplify, this overcomplicates. It obfuscates the reality of your density profile with a series of semi-accurate approximations. And so that a physically informed feature cannot really outperform a physics uninformed feature is fascinating. I think there's a lesson there for all of us. Lastly, I've taken the silicon oxygen interface defined very simply. What is the density drop across the interface, and where is the interface located in radius or in mass? And these 2 parameters should just define ab initio from your initial conditions fed into the same random classifier, give you an accuracy of around 90% in predicting explosion outcome. 2 parameters that you can all calculate, in seconds. And then we repeat this, I'll go over this quickly, repeated the same analysis, but now using an unsupervised approach where we took in our density profiles, fed them into a CNN, a convolutional neural network, as an autoencoder, and then compressed the initial thousands of data points in density versus radial bin in these initial density profiles that we inherit from codes like Kepler or MESA, so revolutionary codes, compressed this to an embedding dimension of around 8, and fed this in with no other physics information into the same classifier. And we get on the bottom row an accuracy around 84%. So this performs second only to the silicon oxygen interface. And so the metrics that have been used historically in population studies of supernovae, of stellar evolution, can be easily superseded with more physically informed metrics like the silicon oxygen interface that perform better and are easier to calculate. And I'll say a few words on the last point here. We also did some label propagation. We took our initial data set of 100 models. This is the biggest sample sizes that we have in the core collapse context. Cut it down to around 50, and then around 25 models, so cut it by 50% to 75%, and then propagated the labels, whether it explodes or not, within the phase space of explosions. And doing so with linear propagation only gave us a marginal improvement around 5% in predicting explosion outcome because the phase space here of density profiles and outcomes is not very continuous. So 90% accuracy with a simple metric. See, I'm being on time. Okay. So I have around 5 minutes left.
About, yeah.
Okay. So I'll zip through the rest. We repeat this right now with an ongoing project
Maybe
with
a bit
collaborators.
longer. I mean, we'll ask questions, so.
Okay.
Yeah.
So we repeat this analysis with now ongoing collaborators at UC Irvine and Baldy Pierre's computer science and astrophysics group, where we've taken now 100 models that are now supplemented with additional 500 models from collaborators. We have now around 700 models in 2D and in 1D plus, where the plus means convection is added as an angle average. And not getting into a CNN, but I'll just go through briefly. We've taken for each of these 700 models 4 profiles: density, temperature, electron fraction, and velocity, and feed into our CNN and then predict explosion outcome, where we again get, using just our models alone, around 90% accuracy. Adding in a larger model set, which includes the 1D plus simulations, we can bump this around 94%. This is really the plateau. We can't do much better than this because I'll mention briefly, the phase space of simulations is very stochastic, of progenitor models is very stochastic. And so getting 95% accuracy is great, and I think it's a well-resolved problem. There's not much more science we can get out of this, and we probably can't. This is really a limit here. So I want to just take a few seconds. We've done, and I'm done talking about machine learning for the majority of this talk. I want to now continue this into human learning. Taking what you have now learned almost intuitively about which models explode and which models do not explode, and the presence of a sharp silicon oxide interface located deep inside the star. Can anyone here be brave enough to venture a guess as to which model, 2 models, do not explode in this set? You need a sharp drop in density, a silicon oxide interface located relatively deep inside. Use an explosion out. It's like I'm not terribly brave either, but I will venture a guess if no one else does. The 2 models that fail to explode are the 12.25, which is right here, and the 14. They have tiny interfaces that are just not enough to trigger explosion. These models have large interfaces that are a bit further out, but they're just so steep, the reversal in pressure is enough to trigger explosion. And these models are so steep initially on that there's no gravitational energy to unbind the exterior to the shock, so they'll explode easier. So easy to explode, difficult to explode, easy to explode. And largely because they have a weak silicon oxide interface. You have a small drop in density, you have a small drop in ram pressure. That's it. I'll now talk a bit about, I will now say it's easy enough to say that progress in supernova theory is limited in large part by limitations in these 1D Kepler evolutionary models we take in as our initial conditions. And so that's exactly what I'll do. Supernova theory is in a large sense held hostage to these limitations. And I'm happy to talk more about this in detail, but this is what sets the floor in predictive accuracy of explosion outcome. In the last 2 minutes, if I can take a few minutes.
Sure.
Yeah. I want to talk about what's next. So we have simulations after 5 seconds. We don't have observations at 5 seconds after core bounce until we see neutrinos and gravitational waves. And so to address this issue, I've developed a framework that couples the early evolutions of core collapse on second time scales to post-breakout properties of the emergent structure. This is now in a paper that's submitted to will be submitted to the archive this week. You'll see it later next week. But the idea here is to take these 5-second simulations and see what they look like at dates. And we have this for a model. We have this for now a dozen models. I'll go through this in a collage. This is a 9 solar mass model at 5 hours. You can see the shock forming. You see these structures in the interior behind the spherical shock are very asymmetric nickel distributions. After a day, a reverse shock forms and pummels inward and destroys the early asymmetries and nickel features. There's none of this nickel formation left after the reverse shock pummels through. Similar for the 11, asymmetric, reverse shock asymmetries are destroyed. The idea here is to sort of pivot ourselves from observations like those of Cas A done by Dan Milosavljevic this year to see if we can reproduce the features you see here, plumes, bullets, tendrils, voids, and so on in our simulations. Now a 15, which preserves asymmetries, you see these cascaded patterns of radial stabilities, almost like waves. A 17 solar mass model, a 20, where now you see the nickel in the 20 is highly asymmetric. You see this elephant's foot of a nickel that extends out to millions of kilometers. And then for a 23, this nickel tripolar balloon has a radial extent of 10 billion kilometers on timescales of weeks. These structures are preserved, and we'll be able to observe these asymmetries. We have a bunch of movies done here, and this is work done with an undergraduate at the Terry Ocean at UC San Diego. But we also have the first 3D core collapse, 3D explosion, 3D light curves, and spectra. This is done with Dan Case and Berkeley. And I do want to overplot this. This is for a low energy explosion. In the black, we show the spectra in red compared to an observed spectra of supernova 2005 CS. And here we're showing the variation by viewing angle. There will be a large variation by viewing angle. We see asymmetries in the nickel profiles. As they change the line of sight of the peak shock nickel, which you saw a few minutes ago, your nickel line, in this case, your iron, the decay products of nickel, iron lines will change drastically with viewing angle. This is not appreciated, how severe asymmetries through the effects of viewing angles are in the core collapse to breakout context. I'll come to a conclusion here with the following nuggets of perhaps wisdom, perhaps not. In the next years, we'll have hundreds of models like the ones I showed you. They will be the best in literature. But on the flip side, they will be the best they can get. This is the best big data we can do in core collapse simulation studies. Dozens, hundreds, maybe up to 1,000 models in a decade. And so, given such a limited but growing training size, how can you then be informed about here I put up 4 key questions. How do you transition from this early classification of explosion outcome to parameter estimations? How can you accelerate these models with clever implementation of neural networks? How can you then pipe these simulations directly into galaxy scale simulations? And lastly, given this growing body of detailed multidimensional radiation hydrodynamic simulations from bounds to breakout, how can you first predict explosion properties and second, template multi-messenger supernova signatures to forge a more intimate connection between supernova theory and supernova observations? Thank you. Yes.
Whether or not something like this, but could you describe how so like the 8-dimension diagnostics, there's better jobs predicting than the other, but what does that mean?
Yeah, I'm sorry, let me clarify that. The autoencoder in this case is only used to compress the dimension of the inputs. The autoencoder result is 8 embedded dimension is then fed into the same random classifier as part 1. Yeah.
Wow. Oh, good. Okay.
I have a follow-up to
Yeah.
that. So you're saying that, yeah, you're taking the betting and doing the random forest. And so when you get better performance by putting the features that you know are good.
Yes.
And what is the dimensionality of these 2 features that you get 89%?
This
MSIO and
yeah, it's
delta?
2 dimensions. These are 2 parameters. These are 2 parameters, not dimensions, 2 parameters.
And that information is included in your input for your autoencoder?
No, it's included for a random classifier. The autoencoder only takes in the initial conditions compressed down to 8,
Wait, the initial conditions,
which is our density profile.
but that information is encoded in the initial condition, like you could derive that from there?
Yes.
So is it just a matter of training it more, or like
Yeah.
you would imagine that you could, like maybe you're helping it by giving it the digested
Right.
information, but in principle, it should be.
If you train more, yeah. So the difficulty is you can't do much better than 93, 94% because I skipped over this, but here are 2 models, 3 models with very similar masses, 14.9 and 15.1, with very different explosion outcomes. And here are 2 models with different masses, similar density profiles, different explosion outcomes. Here, which is inherent stochasticity, that's just the upper limit, which you already are close to reaching. Now, if you do train more
I need the autoencoder.
yeah.
Okay.
So if you do train the autoencoder more, are you asking, can you supersede this physics informed approach like the silicon oxygen interface?
Yeah, no, I'm just wondering if it is easy to learn these parameters.
Yeah.
But I get it. So it's easier just to give it what it needs.
Right.
You're saying there's no other thing that could help me.
No, there are other things. You could fit in like everything in there and, overfit the problem and get, 100%
Yeah, of
accurate.
course.
Yeah.
One more quick. Floor.
Yeah, I was just curious, can you also like, for explanations, like, for education, for like the sort of like, or is it, like,
Yes.
the short time to go?
No, you absolutely can. In fact, we just had in the first slide, and we have now these kicks out to breakout, which will be.
They're all small.
No. There we go. Okay, so the kicks here, I'm amongst the nickel masses and other things you can predict, you can drive properties for and go from classification to prediction. But the kicks here can be thousands of kilometers per second, down to tens of kilometers, 80 kilometers per second. So these kicks are all due to the asymmetric explosion, accretion, and gravitational effects. But they can be hundreds of thousands of kilometers.
All right, well, as I said, David's here for a day. He's got a bunch of meetings, but he's meeting with me after this, after he talks to you. So if you want to come to an office to ask more questions, B433, we'll be talking there. Thank you so much. Let's thank him. We're going to move on with the second speaker is Congyue Deng. She is a fifth-year grad student at Stanford on computer science, working with Leonidas Givas. Sorry, no, I said that wrong. It's actually, yeah, Givas, I got it right. And she's also been visiting Carnegie at MIT, and she is also an AstroAI associate. And she's going to tell us today about geometric aspects of machine learning and to what extent neural networks can actually understand basic geometric relationships of the input. So once you're set up, you're welcome to take over. And do you know what's going on here? Oh, there it is. Yeah, all right. Thank you.
Oops, wait, how do I?
If you press Z
So-
to the Mac, there.
No, I think you want to bring that back onto your laptop screen and then press.
If you move it to the other, move it to the other,
Oops,
you know, just move the window that is
oh, I
to
see.
this other one and try. Yeah, there.
Sorry. I don't know how to use this.
No,
No,
Oops.
so if
Wait.
you press, like, do it now again and I'll press Z. Just try to do it.
Oops,
So
no,
it's not.
sorry.
Oh.
We get one next one down.
Oh. Wait, I
I'm
think,
pressing Z. On the word, that's all.
It's really those windows here.
yeah, I don't. Okay.
oops.
Yeah,
Sorry,
no,
Oh, these
I'm sorry, this.
It's okay.
Oh, I see, that works.
How do you,
Okay, yeah.
right?
Yeah, there it goes.
Yeah.
Is that okay?
Does that work? You need a-
I don't know.
Okay,
Perfect.
okay, cool.
Cool.
Thank you
Thanks
so
for
much.
sending this.
And if you want to use this to.
Oh, I see, yeah.
There.
Oh, great. Okay, thank you. So hi everyone, I'm a PhD student from Stanford and I work on machine learning side. I actually have very limited knowledge in astrophysics, but currently I'm like starting a collaboration with Cecilia and also some others from Northeastern and MIT using neural networks with geometric relations to model astrophysics phenomena. So today I'm mostly gonna talk about how to represent and enforce geometric relations in deep neural networks. But I believe that will have a lot of applications in astrophysics. So ever since very ancient time, geometry has been a language for describing physical phenomena. And also, like, for example, there's a well-known Noether theorem which says continuous symmetries relate to conservation laws. And also people have been describing general relativity with Riemannian geometry, the curvatures. This is a meme I really like, where like the bad, basically like when you don't want to get up, the bad for gravity than anything else in the world. So how do we combine them? How do we relate them to machine learning tools? So in the past, like people have been building machine learning tools for a lot of things. For example, for computer vision, you can identify an image whether it's a dog or a cat with a neural network, or it's been used to like process data for many different fields. However, a lot of machine learning frameworks like neural networks, they're mostly developed based on probability theory. So they fit a probability or they fit a curve to your data, and then it tells you some high level features of the data. But most of the time it's just fitting the data. Like probably all of you have been processing a lot of data with your experiments, And you will know that like for fitting curves into the data, you can easily get overfitting or underfitting. But so what actually you want to do, even with with your model, with your hand design model, or with a neural network, is not just fitting the data, but fitting the data with your theory, or fitting the data with something describing what you're trying to learn here. So this is an analogy. So if you equip your neural network with the understanding of geometry, you're not just looking at the data, but you're also trying to observe and measure the data. And to go a little bit further with generated models, which have been very popular in recent years in the machine learning area, and also have been like helping with a lot of scientific problems, is that so analogy here is also like a generated model in computer science. It's like a very nice artist, like they can draw very nice images, they can generate cool videos. But think about that, if you really want to design a spacecraft or a telescope, you find a mechanism for like you can draw figures that are like exactly following the mechanism behind designing such a thing. You like even the world's best artists, you won't let the artist to draw a blueprint for a thing. And also like for experimental data, you want to generate, you want to get those images with them following some actual mechanism instead of just drawing something that are like following the distribution of all the images in the world. So these are like why geometry are important for having them in the neural network, especially for scientific problems. And how do we possibly combine geometric relations or such understandings into neural network learning? So in the past, like in the machine learning development, people have been studying a lot about the feature spaces. And before thinking about the language of geometry, let's first think about the natural language of humans. So people have been embedding the word of humans into the latent spaces, and they have discovered a lot of relations in the latent space. Like these are like latent embeddings of natural languages, and they can see these correspondences, for example, of word tenses or of country capitals. So analogously, can we have similar things for geometric relations in the latent spaces? So for example, you have a point cloud data of the observation, and you apply a SO3 rotation to the input data. Can you reflect similar geometric transformations or group actions in the latent space of a neural network, where the neural network itself is a black box? It has a lot of learnable patterns that can feed into your experimental observations, but still you want to enforce certain geometric constraints to that neural network. So in the past of my PhD, I've been working on a number of projects which have been trying to enforce geometric, actually not just enforce, but also to express geometric relations in the deep spaces of the neural networks. And I've been working on computer vision, so a lot of examples here are actually more computer vision driven. But I'm gonna tell a little bit about like how they could possibly relate to physics. So starting at the very beginning, we've been studying the linear transformations, which where a simple case in 3D is a rotation. And also like if you relate that to another theorem, rotation invariance actually is a conservation of the angular momentum. And for rotation equivariance for a neural network, if you have rotation equivariance itself is a linear transformation, but you want to combine them to deep neural networks, which is a very highly nonlinear function. So what we designed is that, for example, you have point cloud observations of some data, you feed that in your neural network. So you're trying to enforce that if your network only sees this data, you have some outputs corresponding to the input data, and now that you have a totally different data, where your network hasn't been trained with that, can you also have like enforcement that the new data after the rotation transformation, the network output is still the same? So but if you have such things built into the operator of the neural network, even if a very black box thing, you can still enforce certain constraints in the latent space. And also there are like such things about like in other applications with different formats of inputs and outputs. So to think about it, so one of the very early problems doing that is not just about building operators that are rotation equivariant, but also about how to express SO3 group actions in the latent space of neural networks. Like your neural network, most neural networks, you have a feature space like this, for example, 128-dimensional or 8-dimensional, as in the previous example. But most of these things, they're just a latent vector. And how do you even define, like you can rotate 3D point cloud because you can apply SO3 groups on that. to the 3D coordinates, but how do you apply SO3 group actions to the latent space of point cloud? So we did a very simple thing here to modify the latent space of the neural network, but which is very important to representing the group action itself, is that instead of like using the scalar channels, which is 128 dimensional, we propose something called the vector neurons, where you use 3D vector channels. So here is like 128 3D vectors in the latent space. So here, like, because you have the 3 dimension in this like actual dimension of 3D in your latent space, you can directly apply SO3 group actions on that side. And also, if you have more complex group actions of other dimensionalities or other formats, you can still like, you can extend the 3 dimension to other forms. But essentially, like, this additional dimension is for applying group actions from the right, and your network weights can still be applied from the left. So following this representation, we defined a number of different operators for neural networks, where the simplest one is a linear operator, where it's basically it's taking which is a basic building block for most neural networks, where you take linear combinations of the features. So for standard neural network, you're taking linear combinations of the scalars, and now the changes are now you're taking linear combinations of the 3D vectors, where like before and after the SO3 group action, your network output of this before and after this layer is consistent. And also, on top of that representation and such design of our operators, we also define a number of different operators. Basically, they're following the standard neural network operators for building a whole black box neural network. And most importantly, we define the ReLU nonlinearity activation function, which is one of the very important building blocks of more than deep neural networks. Because if you only have linear operators, you can only build linear functions. But if you really want the complex black box, you need nonlinearities in the middle. But for nonlinearity itself, it's pretty hard to maintain the equivariance or invariance, because if your input data change, you're seeing the data from a different coordinate system. And most of these functions, they're defined for the standard Euclidean coordinate system. So what we're tackling this problem is that instead of using the fixed coordinate system of the 3D space, we're learning the data dependent coordinate system. So it's like from the input data features, we learn the direction K. And for standard ReLU, if you recall that, I mean, for career science people, they're all very familiar with that. It's like for any feature about greater than 0, you keep the feature unchanged. And for any feature that is less than 0, you map that to 0. So this is how that nonlinearity is defined. So here we're saying instead of doing that for the standard coordinate system, we learn this direction K from the input data features. And then for any feature above the plane perpendicular to K, we keep it unchanged. And for anything below the plane perpendicular to K, we clip that to the plane. So in such a sense, we're mimicking the effect of standard neural network, but in a rotation equivariant way. And also similarly, we can define other operators, for example, the pooling operator for aggregating data in the neural network, where we also like learn the direction K from the input data, and then along this direction K, we can compute the projection of the input features, and we can take the argmax of those projections. And we also define normalizations, where for a lot of terms here are very much for machine learning people. For example, layer norm, the instance norm, the dropout, which are all very important for building your network for most of the problems. And also the batch norm is also very important, which is, but here the batch norm is slightly different. How much time do I have? So the batch norm is slightly different because it's aggregating the data through a batch. So basically it's analyzing a batch of data in addition to one single data point. So for the batch norm, because we're assuming having possible group actions on the batch of the data, so to avoid averaging things of like under different group actions, we're taking the batch norm on the length of the vector features, which is the type 0 projection of the type 1 features, to avoid like avoid seeing the feature to diminish. And finally, so with all the operators defined in an equivariant way, which are almost directly following the standard definitions of standard neural network, we can easily plug these we can easily plug our feature representations on and also the network operators into standard neural network architectures. So here is a very popular point cloud architecture proposed by MIT actually a couple of years ago, which we can directly do this change, plug-in change with almost no modification to the architecture itself, but like making the network to follow the group actions of SO3. And this is another architecture proposed actually by my advisor a couple of years ago. And also we can directly do this like plug-in change. And here are some examples of that. So basically, this is a reconstruction task where the data observation you have is a point cloud with some Gaussian noises on that, but we want to reconstruct the dense surfaces following that point cloud. So it's really a fitting problem. So on the very left of each group are the training cases where you see the standard, you see like objects following the standard Euclidean coordinates, and you can like fit the curves. You can fit the surface curves from the point clouds. And here, like on the top, the pink one is a standard vanilla neural network, and you can see like after there's rotations applied to the data, you can no longer discover the correct curve from the data. But the bottom yellow one is our network which has rotation equivariance, which means like if you learn to fit data of the following the standard Euclidean coordinates, after the group action, you can still learn to fit the exact distribution of the data. And also like the third column is very interesting because the third column is with data augmentation. So which means at training time, you already apply random group actions to the training data. So your network actually has already seen more data variations with different poses. But still at inference time, if you only have a vanilla neural network, it's very hard for you to understand the group action itself. But with our operators, it's much more stable when you have different variations at inference time.
So can I interrupt with a question?
Sure.
I just want to make sure I'm following. So you're saying, ideally you want the latent space to sort of understand if all that has happened to the input space was some sort of rotation, for example.
Yeah.
Right? And you're saying that a way to do this is by keeping the same sort of neural network architecture, but modifying the operations of the layers, like the real ReLU or the normalization with certain operations, and that would result in the system being able to recognize an object that has been just rotated, even if it didn't see it during training. Correct?
Exactly.
Oh, okay.
Yeah.
Just making sure.
Yeah, exactly.
Okay, thank you.
Yeah, thanks for your question. And also, like this work is for SO3 group. There's some follow-up work from other universities who have been extending the neurals to lead other likely groups with more extended forms. Okay, so that one is for linear transformations. And beyond linear transformations, we've been also studying multi-body equivariance, which I pasted some figures here to show that it might be applicable to, like, for example, two-body problems in astrophysics if you were trying to do some simulations for some like data feeding. So the multi-body equivariance is like if you have observation of the whole system and you're trying to, so here we study the segmentation, you want to segment the whole system observation into different parts, and you want your network to be equivariant to these parts. So the difficulty of this is that the input is only the whole observation of the system, and you want to do this part segmentation itself. But we also want the equivariance to be we also want the equivariance to the group action of the different parts. So this is actually kind of a chicken or the egg problem, because if you already have the segmentation itself, you can definitely define the equivariance because you're defining the group action on the individual parts of the system. But we want to start with the whole, so we also want the equivariance to help with the definition of the parts. So which, like if we have a wrong estimation of the parts, and then you're applying the wrong equivariance, like for example, here is not the group action you actually want, and then under such a case, our network is doing wrong predictions. So how can we tackle this problem to use network to operate to model the multi-body system?
Sonia? So maybe I missed something, but in that case, if you do segmentation, even if you do the segmentation right, and then you apply transformation, it could still not be very physical. Like if you turn that door around a different axis, right?
Yeah.
How do you deal with? Okay, just
yeah, that's a very good question. So basically, So basically within this work, we didn't tackle this constraint case, which I believe is pretty complicated. So like we are more like tackling only the segmentation problem itself and like assuming like free actions of each part like freely in the 3D space. But I think like under such constraints, currently because like with such constraints, it's not even a group action. So from our side, we do have tried some like numerical methods to better to better respect such constraints in the inference of the network, but still for directly baking them into the network might be hard. So yeah, but that's a very nice problem. And so, however, to avoid the chicken or the egg problem, if we really write it down, we can actually formulate it as a fixed point problem. So this is an observation of your system where you want to apply a network to this whole observation, and then like use it to do part segmentation to segment into multiple parts, and then you also want to have equivariance of the parts. So which means like this is a desired output of the network where you want to like predict the parts, for example, as labels or probabilities on this observation system. And also because you also need that as an input to the network, because you need the parts to define the equivariance or the group actions that act to your system. So essentially like this is the final output you desire, and this is also a condition to your network. So essentially this is so desirably, we're hoping that this is a fixed point of the function defined by the network condition on your observation. So instead of directly training a network to do forward prediction, we formulate this to a fixed point problem and do fixed point prediction with the network. And this is exactly the training state, the training function of the network. And for inference time, you no longer have the ground truth segmentation of the system. So you don't know what the parts are and you don't know what the group actions are. So instead of directly doing inference with the ground truth parts, which you don't know, we start with a random segmentation of the system, which is kind of a uniform probability on the whole system. And then we do this finite fixed point iteration on the system to apply the network again and again. And finally, with equivariance of each individual step, we can finally converge the state that is coherent to our training state. So more specifically, we have some theoretical proofs that under certain conditions, specifically when your network leap cheese is less than 1, you have very good fixed point convergence properties. And at the convergence state, it is self-coherent and it is also equivariant to your training state, even though these two states are two different ones. And here are some results or examples of your inference, where at the very, very left are our training states, where you see certain states of that system and you have segmentations on that. And on the right are the iterated inferences of similar system, but under different configurations of the parts. And through this finite fixed point iteration with the neural network black box function, we can do this convergence, where the final convergence state is very coherent to the training one. Okay, and finally, a little bit more complex situation are continuous deformations, or in more strict definitions like diffeomorphisms of manifolds. So for continuous deformations, it's even more complex because for linear transformations and piecewise, and the multibody system is piecewise linear. So for continuous deformations, it's actually infinite dimensional transformations. So the first thing we're trying to do is to linearize these functions under certain constraints, so that it can be better learned, expressed by the tensors and plug into neural network. So specifically, we've been defining the deformations for the diffeomorphisms in the function space and use the functional maps, which is also a paper published by my advisor probably 10 years ago. Instead of like using pointwise correspondences, for example, this point corresponds to this point to this point, we define the transformation as a matrix in the function space, where the function space is all the real value functions on the two shapes. So we map from the function space of the first shape to the function space of the second shape. And specifically under certain assumptions, these functions can be expressed by a linear matrix. And specifically, how do we represent the function space is that we use eigenfunctions of the Laplacian Beltrami operator. So specifically, this operator is coherent to the standard Laplacian operator in the Euclidean space, but more like a manifold form. It's like the Fourier basis, where the spherical harmonic basis. but it's more general form. So specifically, we compute the eigenfunctions of the source shape and the target shape, and then between these eigenbases, we can compute a linear matrix as a functional correspondence between these two shapes. And specifically, we've been trying this method using the features from deep neural networks on images. So why do we want to work with images? Because like images are actually noisy observations of the of what we see in the 3D world. So we want to see like with these noisy observations and some semantic features extracted by neural networks, can we efficiently construct such functional spaces using the Laplacian eigenfunctions, and can we do correspondences between them? And here we can see that on the left, sorry, this is not the right. On the right are the, or left.
It's our left.
Okay. On the left are the features from.
Rotation.
Oh yeah. Yeah, you're right. Yeah, exactly. So on the left are the features directly computed from two different deep neural networks, where the features are visualized using PCAs and visualizing their first three principal components. And on the right are the Laplacian eigenbasis decomposition of these features. And you can see like with the first couple of eigenvalues, they're pretty low frequency features. And then like as the index of the eigenvalues increases, there are more high frequency features. And with the frequency decomposition, we can compute the functional map from the deep features of a neural network following the functional map optimization, which I'm probably not gonna go into details right now. But here are the final optimized functional maps where we tested with different neural network features. And how you can see is like on the top are the full optimization with all the geometric.
1 minute. So.
Oh, sorry. So TLDR is that. So if the map is more diagonal, it's better because such a case you're matching functions of similar frequencies. And also, like we can see that with a functional map, we can have much more consistent global understandings compared to pointwise maps. So one example here is that if you look at the bird, like there's a red region on the neck, but if you look at the target, if you just use pointwise map, you actually cannot find that red region because like here you almost have zero area for the neck region. But if you use a global consistent prediction, you can say like this is a region between the head and the body. So the functional map is enforcing more global consistent predictions. Then finally, one more example is that it can be used to directly transfer heat maps because heat maps themselves are functions. So instead of converting them to pointwise probability maps, you can directly map them in the function space. And I think it's almost there, and some like fun words to.
Yeah, thank you very much. All right, who has questions or comments? Someone?
So I'm just wondering in the last part.
Yeah.
This problem is kind of cross matching the different objects in different images, right?
Yeah.
Because yeah, we are needing to find basically the head of the cat in the input source is also where is the head of the cat in the also in the output source, something like that. Yeah.
Yeah.
Cross matching something in a way.
Yeah.
And these eigenfunctions are extracting some kind of features of these images, which with the matrix conversion that you're doing at the end, it's kind of you're at the end like it's comparing the two images, features extracting from the eigenfunctions. So essentially, my question is, how come we interpret in a general sense these features that are extracted from the eigenfunctions? How they can help us cross matching the objects?
Oh, I see. Yeah, that's a very nice question. I can explain more. So yeah, the function decompositions are for the features of each image. So the top row are the function basis of the first image. The second row are the function decomposition of the second image. And by viewing them as bases and computing the matrix, which is actually a change of basis. So by computing that, we are matching the two images in the function space. And that can be converted to pointwise map by computing, like if you view as like each point on one image as a direct function, And then like it's also in the function space, you can like map that direct delta function with the function matrix. I mean, in practice, it's really a very like Gaussian approximation of the direct delta function.
Okay. Usually this is done just by select object recognition, and you extract some features of those objects, and you train something to see if these objects are the same thing in the both images, right? Something like that.
Oh, I see, yeah.
Like, not in this work, but like in typical deep learning computer vision problems.
I see, yeah, actually, that's a very good point. I should, so basically for computer vision tasks, there are different levels of details I care about. For example, the courses one is like, I just want to see whether it's a cat or dog. Or I want to, like, the final one is like, I want to draw a bounding box between, like, around the cat of the image. Or like the more detailed one is like, I want to do like point-wise correspondence between these two images, like a full analysis of these two images. Okay, so this is the finest version of that.
Could you, to where can you go with fine tuning the similarity between the two? Like, I have in mind, for example, this could be great for figuring out if a fluid that you're observing, like the galaxy, it's not a fluid, but we treat it as a fluid, is in a state that is the same galaxy, like what was the step before in evolution of the shape of that galaxy, right? If you can deform something into something else, could you use this to get that idea to see there's a diffeomorphism between the two, and this is really the same galaxy was elliptical before or something like that?
I feel conceptually definitely. So probably some numerical issue could be that like where people need to be very careful about is that if you're computing the basis decomposition, like for some regions of like very sharp curvatures, it might be numerically unstable. So I think it also depends on like the specific manifold feature of that. But I think if it's overall a smooth manifold, it's very doable.
Because sometimes two galaxies merge and they were spiral and then become an elliptical and something like that. I'm thinking if you could tackle with this.
I see. I feel it's doable, possibly. Especially like here, we're also, if you look at the features extracted by neural networks, they're pretty noisy. Because like the perception of the visual signals is also noisy. So here specifically for functional map, like you can, I mean, the function space is infinite, but we're only taking, for example, the first 50 or 100 eigenbases. This is already like filter out some high frequency noises from the data.
I want to let people off the book if they need to go. If you do,
It's here all week.
yes, Congyue will be here all week, as opposed to David. Unfortunately, he was only here today, so catch him if you want to catch him up. But let's thank both speakers today. Thank you. So if you want to stay and ask more questions, please do. Yeah, thank you both. Thanks.